On the former Cambridge tribology course, with only an hour allocated to tribology testing, something had to be left out. That something was abrasion and erosion testing. In an attempt to compensate for this, I included an appendix on the subject in my course notes. This talk is based on a much extended version of this appendix. The talk draws heavily on the work of Professor Ian Hutchings at the University of Cambridge, Professor Mark G at the UK National Physical Laboratory, and others. In abrasive and erosive wear testing, although the size of test samples may be small compared with real-life applications, satisfactory data can only be generated by matching conditions within the real-life process. Hence, these are effectively real-life and not scale model test devices. It is not possible to extrapolate wear response from one type and size of particle to another. Tests rely on close control of particle size, shape, hardness, and fracture toughness, and this can only be achieved by careful sourcing and grading of particles. Abrasive wear occurs when material is removed from a surface by a cutting action or by a process of multiple indentations from abrasive particles. This may be an intended process, as in component manufacture, such as in grinding or polishing, or unintended, as may occur in machine operation, such as the wear of digger teeth when working in gravel. Erosive wear involves the removal of material from a surface by impact of a liquid or of a stream of hard particles carried in a fluid flow. There is also cavitation erosion, which is caused by the collapse of low-pressure vapor bubbles onto the component's surface. I will not be covering cavitation in this presentation. As with abrasive wear, erosive wear may be an intended process, as in shot or sandblasting, or unintended, as in the erosion of pipes, solar panel coatings, and other surfaces. Some surfaces, for example wind turbine blades, may be subjected to water droplet erosion. A number of standards exist for abrasion and erosion testing, usually specific to a material or product group. Abrasive wear involves the presence of small, hard particles and sliding surfaces. The particles may either be fixed to a counterbody, as in carborundum paper or a grinding wheel, leading to two-body abrasion, or be loose and free to slide and roll between two surfaces, which is usually termed three-body abrasion. Abrasive wear can involve both plastic flow and brittle fracture. Under some circumstances, plastic flow can occur alone, but both sometimes occur together, even in materials conventionally thought of as brittle. The simplest models usually assume that either plastic flow or brittle fracture is the dominant wear mechanism. The conditions of abrasive wear are further classified as either low stress, in which the abrasive particles are relatively undamaged in the wear process, or high stress, where the particles experience extensive fracture. Somewhat confusingly, three-body abrasion can give rise to the equivalent of two-body abrasion if the particles are dragged through the contact without rolling, as opposed to rolling through the contact. The former gives rise to grooving or sliding abrasion, and the latter to rolling or polishing abrasion. The fewer the particles in the contact, the higher the load per particle, and the greater the tendency for for a particle to become embedded, either temporarily or permanently, in the softer surface and then be dragged across the harder surface. As the number of particles goes up, the load carried by each particle goes down, and the easier it is the particles to roll. The simplest types of two-body test systems are those using either abrasive paper or abrasive grinding wheels, with a test sample in sliding or sliding rolling contact with the abrasive surface. In these rigs, the principal problem is controlling the condition of the abrasive surface. If a pin-on disc test is carried out with abrasive paper attached to the disc, the paper rapidly degrades or becomes clogged with wear particles. Indexing the pin across the disc in a spiral pattern, ensuring that fresh abrasive comes into contact with the pin at all times, overcomes this problem. Another arrangement is the indexing block or cylinder on abrasive drum. The Tabor rotary platform abraser is a long-established industry standard tester for a wide range of different materials. In the abraser, a flat specimen is mounted on a turntable, which rotates on a vertical axis. Two abrasive wheels are loaded against the specimen surface on horizontal axles, offset from the center of rotation of the turntable. As the turntable rotates, the wheels are free to rotate, producing rolling sliding, which results in wear. The ISO standard 23233 rubber, vulcanized or thermoplastic determination of resistance to abrasion using a driven vertical abrasive disc is a standard test used for tire rubbers. This standard test involves loading a rubber wheel sample against an abrasive disc with an imposed load and slip angle. Hence the geometry is similar to the Tabor abraser, but with the specimen and abrasive components switched round. Tests on candidate samples are used to determine comparative wear rates, and as stated, the method is recommended for abrasion tests for various rubber products, especially tyres. Free particle abrasion test rigs typically comprise a stationary specimen loaded against a rotating disc or drum, with abrasive particles introduced into the contact, either dry or with a liquid transport medium. The use of hopper feed systems for abrasive particles improves the uniformity of supply, which in turn enhances control of the particle loading in the contact. In order to avoid contaminating the abrasive particles, whether dry or wet, with wear debris from the test specimens, plus to avoid particle comminution, it is normal to use a single pass system and not recirculate and reuse the abradant. The most widely used test is Astm G75, standard test method for measuring abrasion using the dry sand rubber wheel apparatus. In this test, a sample is pressed against a rubber-rimmed wheel as silica abrasive is fed from a hopper via a nozzle above the converging inlet between the sample and the wheel. There are several limitations to the standard, and these are that the specimens are relatively large and the test is of relatively long duration, requiring perhaps 3 to 4 kilograms of abradant per test. The standard only specifies one abrasive type, Ottawa sand, which is not realistic for many applications and not necessarily suitable for testing very hard materials. The properties of the wheel rubber have a major effect on the results. There are numerous loose slurry abrasive test systems, of which the most familiar will be Astm G75, standard test method for determination of slurry abrasivity, the Miller number, and slurry abrasion response of materials, the SAR number. Astm G105, the standard test method for conducting wet sand rubber wheel abrasion tests, and Astm B611, standard test method for determining high stress abrasion resistance of hard metals. Astm G75 is a reciprocating test in which a deadweight loaded specimen is moved against a bed of abrasive slurry contained in a tray, with the specimen lifted out of contact at the end of the stroke. This allows the slurry bed to reform before the next sliding stroke. Attention may be required to ensure consistent mixing of the slurry as the test proceeds. Astm B611 is frequently used to test hard metals used in mining applications. A sample is pressed against a rotating steel wheel, partially immersed in a tank of slurry. The abrasive specified in the test standard is alumina, which is far harder than the abrasive particles likely to be encountered in the real-life application. Astm G105 uses similar test geometry to Astm B611, but with a rubber-rimmed wheel as opposed to a steel wheel. With both B611 and G105, abrasive particles may pass through the wear interface more than once, so comminution of the abradant may take place. An alternative to the ASTM dry and wet specimen on wheel test configurations is one in which the specimen is mounted horizontally and loaded onto the top of the wheel. The abrasive particles are then fed via a chute to be delivered onto the surface of the wheel immediately in front of the contact. The rate of delivery of particles is controlled by a precision feed system, giving accurate and repeatable feed rates. The problem of particles falling past the contact, as with the standard G65 configuration, is avoided. For slurry tests with this horizontal specimen configuration, particles are fed as for a dry test, but with liquid fed onto the wheel surface immediately before the end of the chute. Liquid and particles then mix on the wheel surface immediately upstream of the contact. Having moved away from the standard geometry, there is also potentially some merit in moving away from the standard wheel materials, in particular for those tests with rubber rim wheels. The effect of rubber hardness and composition on the wear mechanism is well documented, and the difficulty of sourcing standard compliant rubber wheels for G65 in particular has been a long-term issue. There is some merit in devising systems that, instead of using expensive purpose-made test wheels, use smaller diameter rubber tyre rollers of the type used in conveyor systems. These can typically be purchased for as little as $10 per roller. For what is essentially a comparative test, it should be relatively easy to establish the equivalence between a test in accordance with the standard and tests as performed on a modified device. One final point to note with regard to the G65 test wheels is that the sliding speed affects the bulk temperature of the rubber, which in turn affects its hardness and its subsequent interaction with the abrasive particles. To run the actual procedure, it is important to ensure that the wheel cools down between test runs. When running with reduced diameter rollers, it is sensible to run at reduced sliding velocities to minimize unwanted heating. It follows that these tests have to be run with much reduced particle flow rates, hence requiring a precision feed system. For testing thin coatings, using abrasive particles that are orders of magnitude greater in dimension than the coating thickness will produce the equivalent of a sort of multiple contact random scratch test. The thickness of the coating limits the depth of material that can be removed before the coating is penetrated, and once penetrated, the subsequent wear rate is then dependent on the wear performance of the substrate, not the coating. Ball cratering by microscale abrasion has long been used as a means of measuring coating depth, and there are established means of relating wear sky dimensions to coating thickness. The measurement requires penetration of the coating through to the substrate. For wear tests, the same procedure is used, but the wear process is stopped before the coating is penetrated. It is important to note that the microscale abrasion test, depending on slurry concentration, can produce both two-body abrasion, in other words grooving wear, and three-body abrasion, polishing wear. At low concentrations, the applied load is carried by a smaller number of particles, such that the load on each particle is high, causing said particle to be dragged through the contact without rolling, thus producing grooving wear. At high concentrations, with the applied load carried by a larger number of particles, the load per particle is low, allowing the particle to roll through the contact, producing polishing wear. Journal bearings, except during startup, are essentially designed to operate with comparatively thick lubricant films between the loaded surfaces. Transit of particulate contaminants through the bearing gap can give rise to different wear mechanisms, each producing different wear rates. When the size gap ratio is small, worn surfaces may consist of a large number of small pits and indentations, usually with no obvious orientation in the direction of relative sliding, indicating either free movement of particles through the fluid film and subsequent impact with the surfaces, or the rolling of lightly loaded particles through the contact. In both cases, the actual load on the bearing is of no relevance other than as a mechanism for setting the bearing gap. This mechanism, perhaps similar in nature to conventional polishing wear, has been termed tumbling wear. With polishing wear, we would expect the free particles to roll through the tribo contact in continuous contact with both sides. The term tumbling is used to describe the situation in which particles are not in continuous contact with both surfaces, but are free to tumble through the bearing gap. Above a certain size gap ratio, the particles are no longer free to roll through the contact, instead being dragged through, generating grooving wear. As with the pitting wear mechanism, the actual load on the bearing is of no relevance other than as a mechanism for setting the bearing gap. It will be apparent that the load on a particle will be a function of the size gap ratio, the relative hardness of the particle and the bearing surfaces, and the number of particles sharing the load. It is not a function of the load on the bearing itself. For surfaces of similar hardness, grooving wear may occur on both surfaces of the tribo contact. For surfaces of different hardness, there are two possible mechanisms that may not be mutually exclusive. If the surface roughness of the harder surface is sufficiently large, particles may become trapped by asperities and be dragged through the contact, producing grooving or micro-machining wear of the softer surface. However, increasing the hardness ratio between the two surfaces may cause hard particles to become embedded in the softer surface, resulting in more severe grooving wear on the harder surface. The critical parameters for an adequate test model are therefore a test configuration that allows precise control of the bearing gap, and means of introducing abradant particles of carefully controlled shape and size into the contacts. These conditions can be met with a foil bearing rig. It will be noted that the load, either static or dynamic, is not considered of importance, except in as much as it may provide a mechanism for setting the bearing gap. For tests on actual journal bearing components, the key challenge is the injection of particles in a controlled fashion into the test bearing. As with any tests involving abrasive particles, there are uncertainties associated with how long the particles remain in the contact and how long they avoid comminution. Ideally, one would like to control the total mass, size and angularity of the particles passing through the contact. One way of achieving this is to machine a small pocket in the in-running side of the loaded bearing shell and insert a known quantity of well-calibrated abrasive particles held in place with a suitable wax. As the bearing runs and heats up, the wax melts, releasing the particles into the contact. As with many other types of wear test, attempting to accelerate testing by increasing load and or speed risks precipitating changes in wear mechanism such that it is no longer a match for the wear process in the real system. There may also be time-dependent wear transitions following the accumulation of surface damage. Solid particle erosion is the process of removal of material from a surface by impacting particles. In a gas jet erosion rig, depending on the angle of instance, the vast majority of impacting particles can be assumed to hit the target and dissipate their kinetic energy in generating wear or surface fatigue. The majority of particles impact the surface. This may be slightly reduced when the particles impact normal to the surface, because some particles in the jet may impact rebounding particles. In effect, these incident particles are prevented from reaching the target surface. In real processes, for example a two-phase flow in a straight pipe or bend, the particle flux may be much higher than the concentrated jet in the bench test, but the number of particles actually impacting the pipe surface will be much less, and, of those actually hitting the surface, the loss of kinetic energy may also be much less. The particle flux density and velocity in the pipe will vary across the stream, with the profiles dependent on whether the flow is laminar or turbulent. Modelling the particle properties, concentration and velocities, in a real flow system is a complex CFD problem, especially when it comes to modelling the behaviour of particles in the boundary layer, where drag forces may have the tendency to slow the particles down before they reach the surface. Erosion is normally expressed as mass of material lost from the surface divided by the mass of impacting particles, with mass loss increasing linearly with mass of erodent from the start of the test. It is important to note that under certain circumstances there may be a significant incubation period before wear commences. The use of hopper feed systems for abrasive particles once again improves the uniformity of supply, which in turn enhances control of the particle loading on the contact. Careful attention to particle entrainment, distribution and velocity distribution is essential to the generation of repeatable results. There are a number of key factors to do with choice of particle and particle stream that affect the wear process, including the particle impact velocity, particle impact angle, particle mass, size and shape or angularity, and particle relative hardness compared with the surface material. With gas jet erosion, the erosion rate under steady state conditions is normally proportional to the impact velocity raised to the power n, where n is a number typically between 2 and 3. There are two basic erosion mechanisms depending on the surfaces impacted: brittle and ductile erosion. The erosion rate for the former is typically at a maximum when the particle stream is normal to the surface, and for the latter at an angle of incidence typically of between 20 and 30 degrees. There are various established erosion test rigs, of which the most common is the gas blast erosion rig specified in Astm G76, the standard test method for conducting erosion tests by solid particle impingement using gas jets. Astm G76 specifies a short and small diameter nozzle, 1.5 millimeters. This arrangement results in a non-uniform particle flow and a divergent particle stream. As the rate of erosion is dependent on both particle velocity and angle of incidence, this is not entirely satisfactory. Particle flux has a large influence on erosion rates and may well explain the variability observed in many interlaboratory tests. To overcome this weakness, a number of machines have been made with much longer and larger diameter nozzles, allowing equilibrium flow conditions to be established. This results in more uniform particle flow, both in terms of velocity and direction, hence more uniform particle flux. Because of the requirement to entrain and accelerate particles to form a jet, there is a minimum gas velocity at which these devices can be made to work. This is typically about 25 meters per second, hence to run tests at much lower velocities, a different approach is required. A suction wind tunnel rig will allow lower impact velocities and lower particle flux. Such rigs are normally quite large and with significantly dispersed particle flows impacting large targets. Particles are fed from a hopper system in the inlet contraction of the wind tunnel and accelerate under a combination of gravity and air velocity. Because of the large size and expense of the test rigs, wind tunnel methods are used predominantly where information on the performance of shape components such as canopies and wind turbine blades, etc., is required rather than for study of material response alone. As impact velocity is a very important variable in erosion, accurate measurement of particle velocity should be an essential requirement. Various methods of velocity measurement have been employed, including laser Doppler, time of flight between transverse light beams, and high-speed multi-flash photography. All these require sophisticated instrumentation, plus the ability to produce very low-density particle streams. A less accurate but simpler method is the rotating double disc method. This tends to underestimate the particle velocity compared with laser Doppler, but does work with a particle stream of standard test density. It does, of course, require a non-divergent particle stream. In this method, two discs are rotated on a common shaft under the gas jet. The disc nearest to the nozzle has a thin radial slot. Two erosion scars are formed, one with the disc stationary, with the particles passing through the slot in the upper disc, and the other with the disc rotating at a known speed. The angular displacement between the two scars is measured and is used to calculate the time taken for the particles to travel the distance between the two discs. Burner rigs are used to test materials for gas turbine applications. The rigs are designed to replicate the conditions experienced by materials in gas turbines and typically comprise a combustor fed with jet fuel and compressed air with an injector for abrasive particles. Mach numbers at the nozzle exit are typically in the range from about Mach 0.3 to Mach 1, and temperatures up to 1200 centigrade are achieved. As far as I'm aware, there are no standard test methods for slurry erosion, and numerous devices have been used to model different slurry erosion processes. Here are just a few examples. In a Slurry Jet Erosion Rig, a high velocity free jet of solid liquid mixture strikes a flat specimen at some adjustable angle. The system comprises a pump, particle feed system, mixing chamber or amplifier, and circulating systems. These rigs are in effect the liquid equivalent of a gas jet erosion rig. The disadvantage of this type of rig are that the pump and valve life is dependent on the erodent used and may be unavoidably compromised. There is a free as opposed to an immersed jet in the design, and the use of a slurry pump makes this a potentially expensive solution. The advantages of this type of rig are that the angle of incidence is fully controllable and the erodent flow can be measured by time collection of flow in a measuring vessel. In the Slurry Pot Erosion Rig, specimen rods of circular cross-section fixed to the ends of an arm are rotated in a circular container filled with slurry. The disadvantage of this type of rig is that particle flow past the specimens is indeterminate and cannot really be quantified, and the particle impact angle cannot be controlled in a meaningful way. The advantage of this type of rig is that it is simple and relatively cheap to make. The Coriolis erosion tester comprises a rotating arm with a central slurry feed and radial tubes or channels, with specimens mounted in the walls of the tubes or channels facing in the direction of rotation. Coriolis acceleration brings the particles into contact with the specimen surface, generating a wear groove. The disadvantage of this type of rig are the particle impact angle cannot be controlled or determined in a meaningful way. High rotational speeds are required, typically about 6,000 RPM, thus requiring significant containment, spindle balancing, etc. And this is not really a low-cost option. Advantage of this type of rig is that these devices are normally single pass without slurry recirculation, with measurable wear generated quickly without problems with erodent degradation. And it's also a good arrangement for modelling erosion in pipe bends. The rotating jet body erosion rig comprises a rotating arm with the jet body immersed in a stirred vessel. The contraction in the jet body accelerates the mixture, which is discharged normally against a specimen attached downstream of the jet. The disadvantage of this type of rig is that the impact is normal to the direction of flow. It should be noted, however, that two-dimensional as opposed to three-dimensional contraction with twin samples mounted in the flow, like a wedge model in a wind tunnel, would allow tests to be formed with a well-controlled oblique angle of incidence. The advantage of this type of rig is that it's simple and relatively cheap to make. In the flow-through slurry erosion rig, fresh slurry is continuously fed into a test container in which slurry is circulated by an impeller. 16 stationary specimens form the walls of the container, alternating metal and plastic, and a standard ultra-high molecular weight polyethylene gear is used as the impeller. The disadvantages of this type of rig are that particle flow past the specimens is indeterminate and cannot be quantified, and the particle impact angle cannot be controlled in a meaningful way. The advantages of this type of rig are it is simple and relatively cheap to make, and it is multi-specimen. In a whirling arm tester, impact occurs between a falling particle or water droplet and a fast-moving specimen attached to a rotating arm. Because of the potentially high tip speeds, rigs often operate under partial vacuum to reduce the effects of aerodynamic heating and turbulence. Tests with water droplets are performed to model the erosion of intermediate and low pressure blades in steam turbines caused by condensation in these stages. The term tribo implies two bodies in contact and mechanical work at the surfaces. Hence, a tribo contact in a corrosion environment combines the effects of both mechanical and chemical wear. This is usually greater than either mechanical wear in a non-corrosive atmosphere or chemical wear in the absence of work of friction. Tribo corrosion occurs when a component is subjected simultaneously to mechanical wear and corrosion. For mechanisms that operate for long periods in a corrosive environment, it makes sense to perform tribo corrosion experiments. However, in some applications, corrosion and mechanical wear processes are not concurrent. For example, an out-of-service system may be subjected to corrosion, but with nothing moving. It may subsequently be moved away from the primary source of corrosion and into operation, subjecting components to mechanical wear. In this case, the wear is not taking place at the same time as the corrosion, but is taking place on parts previously exposed to a corrosive atmosphere. Think perhaps of putting a rusty piece of machinery back into service. Hence, there may be a requirement to investigate either simultaneous corrosion and wear processes, in other words, tribo corrosion, or sequential corrosion and wear processes, perhaps associated with intermittent service of the system. Astm G119 Standard Guide for Determining Synergism Between Wear and Corrosion provides a useful introduction to simultaneous wear corrosion testing. To conclude, successful tests rely on close control of size, shape, hardness and fracture toughness of the abrasive or erosive particles, and this can only be achieved by careful sourcing and grading. For further reading, the following slides have a selection of useful references.